Okay, thank you very much. Let me start my report concerning the desulphurization of petroleum products and sewage decontamination using new advantages of heterogeneous-catalytic. Light hydrocarbons purification is based on mercaptan extraction using alkaline solution with the following regeneration by oxidation of alkali mercaptans to disulfide in the presence of catalyst. So we can see that. So we can see the first reaction is extraction part that is taking place in the column P01, and the regeneration part is taking in the column regenerator R01. Disulfides formed are not soluble in an alkaline solution. They are removed from the regenerated alkali by gasoline extraction, you can see from here. When using homogeneous catalyst dissolved in alkaline, the formation of disulfide extends beyond the regenerator in the pipelines or in the extractor. Disulfides formed are moved in an extractor from circulating alkaline solution to cleaning light hydrocarbons, and therefore increasing the total sulfur content in the purified product. Butyl-butylene fraction of the UFA refinery, one of the refinery of Russia's operation, is treated in the presence of an alkaline solution of carbon sulfur-alkaline up to the residual content of mercaptan sulfur from 5 to 12 ppm weight. But due to the presence of about 200 ppm weight disulfide in regenerator alkaline solution, entering the extractor total sulfur content in butyl-butylene fraction is about 80 ppm weight. The same problem was observed in the Ryazan refinery of Russian operation, while sweetening butyl-butylene fraction performed in the presence of IFCAS alkaline catalyst solution. In butyl-butylene fraction, cleaning from mercaptan sulfur up to 2 ppm weight was contained up to 20 ppm weight sulfur disulfide. It was found that in the regeneration alkaline catalyst solution, immediately after cleaning disulfides, the content of mercaptan was higher by 30–50% here than at the entrance of alkaline solution in the extractor from here to here in the extractor. This confirmed the occurrence of mercaptan oxidation in the alkaline catalyst solution outside the regeneration in the pipelines or in the extractor itself. Similar result using a process with a water-soluble alkaline homogeneous catalyst had been obtained in the Iranian refineries. In Sweden, propane and butane fraction out of mercaptan up to 5 ppm weight, the total sulfur content found by international standard was about 50 ppm weight. And to reduce total sulfur content up to 35 ppm weight, this fraction was subjected to the advanced absorptional purification using zeolite. Due to the tightening of regulations on the sulfur content of automotive fuels to 50 ppm weight by Euro 4 standard and to 10 ppm weight by Euro 5 standard, as well as high octane additives to them that synthesize from liquefied gases, regeneration of alkaline solution is appropriate to maintain using heterogeneous catalysts permanently fixed in the regenerator. For this purpose, we have developed polymer-based catalyst that is produced in the form of packed elements with an exposed surface. The active components of calcium catalysts are solidly supported on polymer, which excludes them from dissolving in the circulating alkaline solution and in the formation of disulfides outside the regenerator. For this purpose, using this catalyst, we have developed the very loose process for liquefied gas purification, see figure 2, which is provided on Lithuania, Mažeikiai refinery on Ukraine, Lysychansk refinery, and the rest in Russian Federation. They are Moscow, Ufa, Omsk refineries for sweetening butyl-butylene fraction, the Novoyaroslav and Nizhnekamsk refinery to clean propane butyl-butylene fractions, and joint stock company Lukoil to clean butane fraction. Experience at the refinery commercial operation has shown the following significant advantages over its homogeneous-catalytic process. First, reduction of total sulfur in the purified product less than 10 ppm weight by eliminating contamination of these sulfides. Reduce operating costs by increasing the lifetime of alkaline solution from 3 months to 1 year, and lifetime of catalyst from 3 months to 10 years. And I think one of the most important things is the sweetening unit's environmental improvements by reducing the volume of sulfur-alkaline waste, reducing the concentration of free alkali, and getting an exception of heavy metals in waste water. Thus, in butyl-butylene fraction sweetened from mercaptans by the Demercaptanization joint stock company Taif & Khan, mercaptan sulfur content is about from 1 to 5 ppm weight, and total sulfur content does not exceed 10 ppm weight. Similar results were obtained in joint stock company Lukoil. The content of mercaptan sulfur in butane fraction less than 5 ppm weight, and total sulfur found by Antec device less than 10 ppm weight. So it was the technology for the demercaptanization of light hydrocarbons. The next technology is for demercaptanization of jet fuel. We call it kerosene sometimes. With the putting into operation of hydrocracker refiners, there were significant amounts of desulfurized kerosene fraction. This makes it possible to increase the production of jet fuel through the involvement of virgin kerosene fraction by manufacturing composite jet fuel TS1 for Russian standards and for international standards Jet A1. To involve the entire volume of virgin kerosene in the composite jet fuel, it is needed to sweeten it from mercaptan sulfur content, which is from 4 to 10 times higher than normal acceptable for jet fuel, 30 ppm weight. In this context becomes actual the process of selective oxidation of corrosive mercaptans into inner disulfide in an alkaline medium at 40–60 degrees Celsius. Estimated capital cost for hydrotreatment of kerosene compared with alkaline sweetening is higher from 10 to 20 times and operating cost from 20 to 50 times. The main obstacle to widespread adoption of the normal processes of alkaline kerosene treatment using base control catalyst is their multi-stage and ecology. The fragility of the adsorptional interaction of porous carbon with an alkaline catalyst solution leads to constant erosion over the long career. This calls for constant feeding of coal and cleaning the fuel from the alkaline solution, which leads to the formation of multi-stage waste at all stages of jet fuel purification. So from the figure 3 we can see that we have the following sewages. Alkaline cleaning of kerosene from acidic impurities, then kerosene water flushing from low alkaline solution, kerosene salt drying from moisture and traces of alkaline solution, and bleaching flake purification from traces of alkaline solution and copper salts. Instead, this process, see figure 4, we propose two-stage regenerative low-waste Demercaptanization method using polymer-based catalyst in conjunction with the promoter that can quantitatively settle in 60–90 minutes. In this case, together with sweetening in the same reactor, promoter is extracting acidic impurities as well as a part of the reaction and dissolved water, which are then picked up while promoting regeneration. Significant advantages of the Demercaptanization process using KSM catalyst and promoter compared with this above process are reduction of capital and operating costs for jet fuel cleaning due to the exclusion of the following units. as I said before, preliminary alkaline treatment of kerosene from acidic impurities, sweetened jet fuel water washing from traces of acidic catalytic solution, kerosene moisture salt drying, kerosene bleaching clay adsorption purification from traces of copper salts. And I think the most important, as I said before, improve the ecology of refinery by eliminating all alkaline naphthenate toxic waste, copper salts, and clay slurry. Experimental batch of virgin kerosene sweetened by a pilot plant of the Moscow refinery by using the Demercaptanization method has successfully passed the qualification test in all Russian Research Institute for Oil Refinery, with 3 major refineries in Russia concluded license agreement for implementation of this process. So the next technology we are going to propose here is about the demercaptanization of gas condensates and light oils. During hydrotreatment of Astrakhan high mercaptan condensate was established that the presence of mercaptans in the feed leads to increase the frequency of regeneration of the hydrotreatment catalyst. The reason is the intense formation of coke deposits by thermal decomposition of mercaptans with polymerization products of the decomposition on the catalyst. The share of this product up to 60% by weight of coke deposits. These data indicate the feasibility of pre-sweetening high mercaptan raw before hydrotreatment. This scheme is attractive in terms of reducing the porosity of the material in case of mercaptan removal that causing intense corrosion of equipment in the heating zones due to the mercaptan's low threshold of thermostability from 140 to 170 degrees Celsius. The share of mercaptan sulfur has a number of fields from 60 to 6 from 40 from 12 to 67 ppm weight. So we can see that for Qatar condensate, for example, we have 65% of mercaptans by weight of total sulfur. For Zanazol oil, Kazakhstan Republic, and others. In nowadays processes of oxidative or extractive oil demercaptanization by alkaline solution is solving only the problem of deodorization by the extraction of following oxidation of light C1 and C2 mercaptans. In order to desulfide and to satisfy necessary requirements and provide acceptable terms of its transportation in Russian Federation or abroad. Thus, for desulfide remain in the oil that is sulfur content in oil is not changed. See table 2. So from table 2, we can see that the use of oil oxidation sweetening completely oxidized only methyl and ethyl mercaptan. The heavier propane fuel and butane fuel is oxidized only by 70%, and butane fuel oxidized only by 20%. The residual mercaptans and desulfides formed remain in the oil, causing corrosion and formation of coke deposits at subsequent high temperature hydrotreatment processing. Because desulfides also have low thermal stability and decomposing into mercaptans and hydrogen sulfides when heated above 200 degrees Celsius. To facilitate the subsequent processing of high mercaptan gas condensate and light oil, we have developed the Demerus process. The distinguishing feature of Demerus is using of special extractant capable of removing mercaptans from high volume hydrocarbons. Extracting second time from the purified gas condensate does not exceed 90 minutes. Aqueous alkaline solution under this condition is not settled even for 300 minutes. As seen from table 3, in case of the Demerus process, gadmium fraction is extracted up to 94%. And 37% with the usual alkaline extraction. from gas condensate up to 67%, of mercaptans against only 13% with usual alkaline extraction. By extracting mercaptan decreases the total sulfur content in the gas condensate that we can see from table 4. Extraction regeneration is carried out by oxidation of contained mercaptans to disulfide using kerosene catalyst. See figure 5. At the same time, decided important task of obtaining by high mercaptan raw disulfide oil, a valuable petrochemical product that is an effective agent for sulfur catalysis of hydrolytic processes and inhibitor of formation during pyrolysis of hydrocarbons. So, and the last technology we propose here is the sulfur-alkaline waste oxidation. We just call it LOCUS. The essence of LOCUS process is oxidized by atmospheric oxygen, toxic sulfide contained in the waste to less harmful oxygen-containing compound, thiosulfate and sodium sulfate, sodium sulfate, and mercaptan to inert disulfide and further alkyl sulfonates by the food reaction 3 and 4. Unlike the original sulfide and mercaptan, from thiosulfate, sodium sulfate, and alkyl sulfonates do not have odor and have much higher limit values for plant biological wastewater treatment. It is easily achieved at the expense of the actual dilution of oxidized sulfur waste with offsite runoff before it enters the biofeed bag. LOCUS process, see figure 6, is taking place in the presence of the kerosene catalyst at 78 degrees Celsius and a pressure of 0.5 MPa. After the complete oxidation of toxic sulfide and mercaptan, the waste is sent to the site of neutralization before discharging into the biofeed bag. To reduce water consumption and to provide circulating water supply, it is appropriate to provide for dissolving oxidized and neutralized waste by known methods such as reverse osmosis. In contrast to the process of sulfur-alkaline wastewater carbonization or liquid phase oxidation method, LOCUS process does not require much heat and chemicals and does not pollute the air emission by hydrogen sulfide or sulfur dioxide. The alkaline nature of the reaction medium and the relatively low temperature of the process allow using apparatus made of carbon steel. So the use of kerosene catalyst in LOCUS process can significantly increase the efficiency of sulfur-alkaline waste decontamination in comparison with carbon fiber oxidation catalyst or non-catalytic method. First, reduce the temperature and shorten the oxidation time of sulfide and mercaptan by air oxygen to provide a deeper oxidation of a sulfur compound and decrease chemical oxygen demand by about 75% and reduce the amount of toxic mercaptans in the exhaust air. So, in the end of my report, let me once more remind our technology that I have tell about. The first one was the sulfurization of light hydrocarbons or liquefied gases, especially for light fuels, the demercaptanization of jet fuel, the demercaptanization of we can call it the partially desulfurization of gas condensate of light oils, and the last one, sulfur-alkaline waste decontamination that we call LOCUS. Thank you very much for your attention. light hydrocarbon demercaptanization is widespread in Russian Federation. For kerosene treatment, we have made a pilot experience in the Moscow refinery. Locus process also was for sewage decontamination was well spread in Russia for sulfur-alkaline waste decontamination. Nowadays, we implement the demercaptanization of light fuel for the Rosneft refiners.
Você retira mercapta de extrações leves, não é um processo que usa solução alcalina. É um outro tipo de reagente.
The demercaptanization of light hydrocarbons, I mean, for them with fractions, is used alkaline solution, and the regeneration that, for example, in Russian Federation, not only in Russia, I think all over the world, is appropriate using different catalysis. And our aim is to use heterogeneous instead of homogeneous, because now it's changed the standards for Euro 4 and Euro 5, and the homogeneous have some critical points of this.
Demercaptanization. Demercaptanization é um processo que usa solução alcalina também.
It's alkaline medium, yes, but medium alkaline.
Então,